Hi, my name is Sophia Galvin, and today I'm going to be presenting our Crank flashlight, which was made through reverse engineering. Let's get started with our design challenge. Our company is losing market share to a competitor's flashlight, so our team was tasked with analyzing their design, identifying improvements, and creating a redesigned product. We developed a new flashlight that enhances performance, usability, and appeal, giving our company a strong opportunity to compete and regain market leadership. For our interviews, we conducted them with our peers and family members to see what we needed to implement in our new product. After I spoke with my peer and wrote what she said, I organized her words using a highlighter to differentiate the importance of every phrase. I then repeated this 3 times with 2 new interviewees. For our affinity analysis, we first made an activity diagram that explains how the energy translates in order to create light. First, it begins as rotational mechanical energy from the movement of the crank, which spins the gears and magnet coil mechanism, and then into electrical energy from there into the wire, the LED bulb, and lastly to light energy into the lens. The action functions questions table we created takes the actions that occur when using the flashlight as shown in the activity diagram and observes the functions that our flashlight must include for proper execution. Lastly, we ask questions to double check that we are meeting all of the requirements and addressing concerns our customers may have. We also made a frequency table to convert our interview qualitative data into quantitative data. This meant that we took the words or comments that occurred the most throughout our interviews and put them into our table and rated their importance after counting their frequency. This helped us understand what feedback was the most important to implement into our new design. For our predictive sketch, I made this sketch when we were first asked to predict what we thought the inside of the pig crank flashlight would look like. I predicted correctly that there would be gears inside, but did not know how the energy would be transferred to the lights, which I then learned was through the use of a magnet coil mechanism. I also thought there would be circuit boards powering the light, which I was incorrect about. Let's talk exploded view and science behind it. Here you can see that we opened up the flashlight to see all of the parts inside and understand the science behind it. We discovered that the crank moves the gears inside, which is connected to a magnet coil mechanism. This magnet coil mechanism consists of a magnet that spins with a coiled up wire around it that produces the energy. The energy can only be produced when the magnet goes a specific direction in which the wire is correctly placed. This energy runs through the wire to the LED bulbs, then shooting light through the bulbs. For testing, we needed to test the flashlight so that we could determine by how much exactly we would need to improve brightness, sound, and more. On the left are images of us using a sound meter and digital lux meter to measure the brightness and sound level of the flashlight. Not pictured, we also used a ruler to measure its dimensions, a force gauge to measure the force needed to use the crank, and our ruler again to measure durability as we dropped it from various heights. On the right, I included a table that consists of our customer interview needs, what tests we performed, the average measurement of our data collected, and lastly, what differences we wanted to see in our own product. Now, what should our new designs be? Now we organize our ideas into a table. This shows what measurements we wanted to see in our product along with what the current flashlight provides us with, shown in the columns on the left side of the table. And as you can see in our design solution, we decided on a 1,000 lumen LED light, better gear layout, improved crank, strong casing, and a compact rocket shape. For C sketching, to start constructing our design, we started with this. Each of my team members drew one design idea that we wanted to incorporate into our final design. I started with drawing a crank, remembering that we would need some sort of solution to our sound issue. I decided to include a sort of insulation material to line the inside of the flashlight, lowering the sound that would escape it. My team member Tatum sketched out design 2, which included 2 AA batteries for more power after remembering that we would need to power more powerful light. These batteries were both connected straight to the light bulb so that they could power the flashlight without the need of the crank for versatile use, while also just increasing the light power for an overall better light. Lastly, my team member Emily A created Design 3, which included a light bulb that would be a 1,000 lumen LED light. She made our pig design into a rocket design for a different and unique aesthetic that would work perfectly as a crank flashlight. One of the fins on the side would act as our crank, fitting in nicely with the design while also staying functional. Our final design and how it works. Our final design is an adaptive redesign, which means that it has similarities but also new product design. Ours has almost the same design, but with one LED light instead of two batteries, an added rocket look, and screws for easy replacement of batteries and the light bulb. Our final design is a rocket-shaped crank flashlight that uses both manually and battery power. User pushes the crank, activating a magnet coil system that spins to generate electricity. The generated electricity travels through wires to help power the flashlight. The flashlight includes two AA batteries, as mentioned before, that store power separately from the magnet coil system. Electricity from either source flows to the LED light bulb to produce light. Side buttons allow the user to choose between battery power or manually generated power. A lens focuses the light bulb onto objects for better visibility. And lastly, a screw-on front piece allows the LED light bulb to be easily replaced. My final design is better than the original because it meets all customer needs, improves brightness, noise, and durability issues, it stays portable, it's the most realistic, and it uses real test data to be generated. Thank you so much.